Hi, so now I want to go through with you a more complicated version of the Atwood's machine problem. So I've already made one video explaining how to solve a simple frictionless Atwood's machine, and in that video the pulley over which the two masses were hung was massless. So the only masses in the problem were the masses of the blocks. In that video I had called them little m and big M. For this problem, we're going to instead consider a massive pulley. So of course anything with mass has inertia, which means it's going to take some force to get it moving. The massless pulley took no force to get moving. This pulley, with mass mp as shown, will take some force to get it moving, which means the whole system will accelerate slower. It'll take longer for the large mass to hit the table, etc. So the questions we're going to want to answer here are, what is the net torque on the pulley? You'll usually see this problem during sections about torque in your physics class. What is the acceleration of the masses? As before, we want to see how fast these two masses are accelerating. mb, in this case, will be the bigger mass, so that one will fall to the table. We want to know what the tension is in each side of the rope, here shown in red. In the problem where the pulley is massless, the tension is the same throughout the rope, because that's the definition of a massless pulley. It just changes the direction of the tension. But in this case, because the pulley will have a net torque getting the mass to start to rotate, one of the sides of the rope will have more tension than the other. 4, how long does it take for the mass mb to hit the table? And 5, how fast is that mass moving the instant that it hits the table? For this problem, we're going to tackle the first few steps the same way as we would have done in the previous problem, which had a massless pulley. We're going to start with free body diagrams and Newton's second law. So for each mass, the mass ma, which is smaller, the mass mb, which is bigger, and the pulley, we're going to draw them and start putting forces on them. The first two forces that you'll note are the weight of each of the masses, ma and mb. And of course the weight in either case is the mass times the gravitational acceleration on Earth, g. And you will also note that each mass has a tension pulling it up from the rope. Previously, we of course labeled these just T because it was going to be the same throughout the rope. But now, because each side of the rope will have a different tension, we will label them according to which mass they're acting on, TA and TB. Now for the pulley, rather than simply considering forces and just drawing them on the free body diagram, what we're going to need to do is consider torques. So of course the pulley has its own weight, but we don't need to consider that because it acts through the center of mass, which is also the center of rotation. So the weight of the pulley does not create a torque on the pulley. But what does create a torque on the pulley is each of these tensions. In the case of the mass on the right, mb, that same tension that pulls mass mb upward tends to pull the right side of the pulley downward. And same for TA on the left. So these are two opposite torques. One is bigger than the other, and we know which one has to be bigger because if mass mb is the bigger mass, then the pulley is going to rotate towards that mass, so TB is bigger than TA. You don't have to know that immediately, but if you just think it through, that makes sense. So again, because we know that TB is the bigger tension and mass mb is the bigger mass, we know that the pulley will rotate clockwise. And so whenever we have something spinning, we want to define a direction of positive rotation. And in this case, that'll be clockwise, indicated here by the purple arrow. And this will help us, for both masses, also define a positive direction when we're adding up the forces on the mass. So Newton's second law says that F net on an object equals the mass of the object times its acceleration. And of course the net force just means add up the forces, but with their vectors, so in the correct directions. So in the case of mass A, we have F net A equals ma times the acceleration. And this, because we're defining clockwise as positive, means that the tension is the positive force and the weight is the negative force. So this is Ta minus mag. And for the mass B, we have F net B equals mb times the acceleration, which is also equal to now the weight being the positive force because it's the thing that tends to rotate us clockwise. So mb times g minus the tension b. For the pulley, instead of using Newton's second law in terms of forces, we need to consider torques. So remember that just like F net equals ma, tau net, the net torque on an object, equals I alpha, where I is the moment of inertia and alpha is the angular acceleration. So the moment of inertia is analogous to mass, and the angular acceleration is analogous to the linear acceleration. And for a torque, the definition of a torque in terms of a force is the r cross t in terms of vectors, r cross f in terms of vectors, and in this case the forces are both tensions. So here we just have rtb minus rta, where r is the radius of the pulley, and tb and ta are the tensions. So now we might want to put in what we know alpha and I to be. Alpha is related to the linear acceleration along an edge of the pulley by this equation, alpha equals a over r. Remember that alpha is measured in units of radians per second, whereas a will be in meters per second, for example. So you can always remember that you need to get rid of the meters, so you need to divide by the radius. And we can look up that the moment of inertia for a disk is 1/2 mr squared. So we can put these in and get that rtb minus rta equals 1/2 m pulley r squared times a over r. And of course we can simplify that, canceling one of the r's, and arrive at this equation. So now what we have is 3 equations and 3 unknowns. For the mass A, we have ma times the acceleration equals the tension minus the weight. For the mass B, we have mb times the acceleration equals the weight b minus the tension b. And for the pulley, we have 1/2 mpa equals tb minus ta after canceling an r through that entire equation. So A is our first unknown, TA is our second unknown, and TB is our third unknown. So 3 equations and 3 unknowns we know we can solve, and that'll be the next. So now we have our system of 3 equations and 3 unknowns, and we're going to write those down here again and pick a variable to solve for. So you can use any of your favorite algebraic methods of solving an equation, system of equations. What I will do is eliminate tension from the problem first, each of TA and TB, and then solve for the acceleration. So if we take our first 2 equations for each of the block masses and solve them for the tension in each side of the string, we get these equations where TA, adding mag to both sides, is ma times the acceleration plus ma times the gravitational acceleration. And for tb, instead of an addition, we get a minus sign, where tb equals mb times the gravitational acceleration minus mb times the linear acceleration. And all we have to do now is plug both of these into the third equation for tb and ta, and we arrive at an equation in only one unknown. So 1/2 mp times a equals tb minus ta. Well, tb is mbg minus mba, and then ta is the sum of maa and mag, so we have to have the minus sign on both of those once we've subtracted it. And now the only unknown in this equation is a. The first step towards solving this will be to bring everything with the a to the same side of the equation. So we have the 1/2 MPa already on the left. We will add the other two terms with the a in them to both sides, and we arrive at this equation. And now everything on the left has an a in it, so we can factor that out, and everything on the right has a g in it, so we can factor that out. And now we divide by the coefficient of a, and we get that a is equal to mb minus ma over 1/2 mp plus ma plus mb, all times g. So this is the answer to one of the parts of our problem, which asked what is the acceleration. This is it in terms of g. You'll see that the whole fraction there in front of g doesn't have any dimensions, doesn't have any units, because everything is in mass, and there's mass in the numerator and the denominator, so it'll cancel out. So we know that our dimensionality is right. But now, this isn't the first answer that we were actually asked for. The first thing we were asked for is what is the net torque on the pulley? Well, tau net equals RTB minus RTA, but we don't know the tensions yet. So instead, we can use the other side of that equation, which says that tau net equals 1/2 MP RA. MP and R are known, so we have to just put in A that we've just solved for, and we arrive at this equation. Tau net equals 1/2 MP R times A, which is MB minus MA over 1/2 MP plus MA plus MB times G. And this is the answer to the first question we were asked. So now we have our first set of answers to parts 1 and 2, but there's still more to solve for, so we need to go back to our two equations for the tensions and get those tensions to be able to solve the rest of the problem. So if we take the two equations that we've already solved for before, TA equals MAA plus MAG, and TB equals MBG minus MBA, we'll notice that the things that are unknown here are the tensions, and we already solved for the acceleration. So on the left equation here for TA, both terms on the left side of the equal sign have an MA in it, so we can factor out that and get A plus G times MA. And similarly for TB, both terms have an MB in it, and you can factor that out and get G minus A. And of course, A is as we solved for before. So we can put that in. Let's start with TA. For TA, we have TA equals MA times this quantity A plus G, where now I've simply thrown in the formula for A that we solved for before. And you'll see that we have MB minus MA over 1/2 MP plus MA plus MB G plus G. So now both terms inside of the parentheses have a G in them. We can factor that out, and we arrive at our final equation for A, for TA, the tension in rope A, where TA equals MA times this quantity MB minus MA over 1/2 MP plus MA plus MB, all plus 1, times G. So again, we can check the dimensionality of this, which means the units that it would have if we were to put in the numbers, and tension is supposed to be a force. Inside of the parentheses here, we have a fraction, which has no units, and then the number 1, which has no units. And then outside of the parentheses, we have the mass and the gravitational acceleration. And we know that force equals mass times acceleration, so we know that this is going to have the right units, so that's a good sign. For TB, the formula is very similar. The only difference is that instead of A plus G, we had G minus A. So we just need to swap those, swap the order, put a minus sign in, and we have TB equals MB times 1 minus the fraction, and then all times G. And these are our answers for the next part of the problem, which asked us what is the tension in each side of the rope. So next, we want to go back to the Atwood's machine problem that we had before and compare to what we had with the massless pulley and say, okay, how long does it take for MB to fall the whole way to the table? So just as before, we're going to start with a kinematics equation, x minus x naught equals v naught t plus 1/2 at squared. And the only unknown here is the time, because we have a as solved for before. V naught is 0 if we release this system from rest, and x minus x naught equals h. So we just have that h equals 1/2 at squared. So all we have to do is put in a from there. We get h equals 1/2 times mb minus ma over 1/2 mp plus ma plus mb times gt squared. Or if we take the 2 and multiply it through the denominator of this fraction, mb minus ma over mp plus 2ma plus 2mb all times gt squared. So we're going to solve this for t. We have to divide both sides by the fraction. So we'll have mp plus 2ma plus 2mb times h over mb minus ma equals gt squared after dividing by the fraction, or that t equals the square root of mp plus 2ma plus 2mb times h over mb minus ma times g. This is how long it takes for the mass b to fall and hit the table. So just to compare to the solution from the massless pulley, we see some similarities here, where t was the square root of 2h over the sum of the masses times the sum of the masses over the difference in the masses times g. So now we have h over g again, and we have this fraction of masses, but in the numerator we have the mass of the pulley included plus 2 times the mass of each of the blocks. So the time for the massive pulley is bigger. In the denominator we have the same thing, the difference in the masses. So because we've added something to the numerator, the time it takes is longer than with the massless pulley, which makes sense because it takes more time to get that pulley rotating. Now on to the last part of the problem, to find the speed of block B when it hits the table. So again, we'll start with a kinematics equation. Recall that v equals v naught plus at, and that we've already solved for the acceleration of the block and the time it takes for the block to hit the table. So again, we're releasing the system from rest. V naught equals 0. So we have v equals at, and all we have to do is put in our solutions for the acceleration and the time to finish the problem. This again is the full solution. You could put numbers in here and be finished. Here's the acceleration, here's the time. So also if you've already put in numbers for those, all you have to do is multiply them. If we want it in terms of variables, we can do a little bit of algebraic simplification. The first thing to note is that we're going to bring the fraction outside into the radical, and so there is some simplification to be made if we have the same terms in the denominator of the outside fraction and the numerator of the inside fraction. They're going to end up canceling a little bit. So we'll factor a 2 out of the numerator of the inside fraction. And now when we bring in that outside mb minus ma times g over 1/2 mp plus ma plus mb, we square everything. The g from the denominator inside the radical cancels, and the fraction denominator cancels the numerator inside, and vice versa, but of course we have one of each thing left over. So we have that v equals the square root of 2h times mb minus ma times g over 1/2 mp plus ma plus mb. This is the final answer to our problem, but one last thing, we want to compare this to the solutions from the massless Pulley Atwood's machine. So there we had v is the square root of 2h big M minus little m times g over the sum of the masses. Here we have a very similar situation. We have 2h times g in the numerator, we have the difference in the masses, and we have the sum of the masses. And we've added the mass of the pulley to the denominator, so this velocity of the massive Pulley Atwood's machine is going to be smaller than that of the massless Pulley Atwood's machine. That's it. Thanks.